Okay, so continuing our discussion on chemistry of conjugated dienes. So we've looked at UV-based spectroscopy. We've looked at kinetic versus thermodynamic addition of across a conjugated diene. So now what we're going to do is take up pericyclic reactions. So these are three classes of reactions that share features. We spend more time on one of them, less time on the other two. So let's get going with the first one. So again, to remind you, what we're actually doing here is we're covering pericyclic reactions. There are three types. So the first type would be your Diels-Alder reaction. That's the one we spend the most time on. And your classic example, right, your very, very basic Diels-Alder reaction would take 1,3-butadiene in a specific conformation, we'll discuss that, react with something like ethene, and you're going to get, so I'll put numbers here, 1, 2, 3, 4, 5, 6, and I recommend that until you become good at this, that you always label your carbons to keep track, otherwise you're liable to miss some or add extra. So carbon 4 will take the pi electrons and form a sigma bond with carbon 5. Carbon 6 will take the pi electrons and form a sigma bond with carbon 1, and the pi electrons here are going to change location and now be between carbons 2 and 3. So what you end up forming here is going to be cyclohexene. The second type of pericyclic reactions that we'll cover are what we call electrocyclic reactions. In electrocyclic reactions, what we have is situation like this. So again, I'll put numbers so that we're keeping track of our atoms. So if you, and again, there's going to be some heat involved here, some heat or possibly light. And what's going to happen here would be carbon 6 will take the pi electrons, form a bond with 1. These pi electrons move over to now be between 2 and 3. And these pi electrons move over to now be between 4 and 5. So if you follow that, then what you're going to get is going to be the following, right? So here's 1, 2, 3, 4, 5, and 6. So you see where things have actually, bonds have broken and bonds have formed and bonds have shifted. So it would be an electrocyclic reaction. And then finally, you have what we call sigmatropic rearrangements. You've actually already seen a sigmatropic rearrangement in Orgo 1. We just didn't call it a sigmatropic rearrangement, but a sigmatropic rearrangement would look like this, where I would have here, let me just scroll slightly higher. So what we were going to have here is going to be this type of a situation. So 1, 2, 3, 4, 5, 6. And so what's going to happen here is 6 takes the pi electrons, forms a bond with 1, sigma bond. These pi electrons move over, and these sigma electrons move over, so you break the carbon 3 to carbon 4 bond. Again, a little bit of heat here. So I've broken the 3 to 4, so I'll start at 3. There's now going to be a double bond with 2. There's now just a single bond with 1. There's a new sigma bond between 1 and 6. There's just a single bond between 6 and 5. And there is a new double bond between 5 and 4. They share certain features you can look up in the client textbook, for example, what they tell you about the features that they share. and any differences that you might have. So we're going to take up Diels-Alder reactions first. All right, so Diels-Alder reaction. Excuse me. Diels-Alder reaction. This is also known, by the way, as 4+2 cycloaddition. So let me remind you again what I just showed you. This would be a Diels-Alder reaction, where you're going to have this 1,3-butadiene reacting with this ethene. You're going to get your electrons flowing this way, and you're going to end up getting cyclohexene as your product. 1, 2, 3, 4, 5, and 6. All right. So what are some of the things that we have to note here? First of all, this side, this reagent is what you call a diene, and this one is what you call your dienophile. So second thing that I want to highlight is, so you see 3 arrows. So which is the first movement of electrons? So the first movement of electrons will be either 4 to 5 or 6 to 1. Both of them will work out the same way. So in other words, this is the first step. This one here, where 4 takes the pi electrons and forms a sigma bond with 5. So that is the first step. The reason why that is important to note is that then, in a sense, you can think of the diene as acting as a nucleophile, as an electron-rich species that is pushing electrons towards your electrophile, which is a dienophile, which is the electron-poor species. So in other words, you want your diene to be electron-rich because it's the one that starts the reaction and pushes the electrons towards a dienophile. And if your dienophile is accepting electrons, clearly you don't want it to be electron-rich, because if you're pushing electrons towards an electron-rich species, then you're going to start getting repulsion. So you need your dienophile to actually be electron-poor. So once you understand that this is how the reaction occurs, and therefore the nature of the diene and the nature of the dienophile, then you realize, okay, that's just your basic diene and your basic dienophile on the screen. Can I add things to them to enhance their reactivity, to make the dienophile more reactive, to make the diene more reactive? So yes, we can. What types of substituents would we want to have on the diene and the dienophile? Well, if I want my diene to be electron-rich, I would want to attach substituents that are going to push electron density towards the core of the diene. So the core of the diene would be that part. So anything that we add to that part, we would want it to actually push electron density towards that core to make it more electron rich. And clearly the opposite is going to be the case with the dienophile. Anything that we add to it, we would want it to actually pull electron density away from the diene to make it electron poor. So then let's look at examples of good dienes and good dienophile. So in the case of dienes, if I want to have substituents that are going to push electron density, think back to your orgo-1. Can you think of any kind of substituents that would be good at pushing electron density towards something? And then you think back of carbocations, and you know that a tertiary carbocation is more stable than a secondary is more stable than a primary. So I'll just remind you very quickly. If I have a carbocation here, and I have a methyl carbocation, you already know that's very unstable. Then I can have a primary, which we know is going to be a little bit more stable. then we can have a secondary, which we know is going to be way more stable than the primary. And of course, then we can have the tertiary, which we already know is going to be the most stable that we have. So as I'm going from left to right here, I'm getting increased stability. And when we were examining this in Orgo 1, we asked the question, why do we get that order of stability? And we offered two reasons. I'll pause for a second, see if you can remind yourself and think of what those two reasons are. So I'll give you the one that is relevant to this. We said that one reason why you get this order of stability is that alkyl groups, things that are carbon-based like a methyl, they're very good at pushing electron density. So the methyl doesn't have any. The primary has one that's pushing electron density towards the carbocation. The secondary has two that are pushing electron density towards the carbocation. And the tertiary has three of them. And why is pushing electron density towards the carbocation making the species more stable? Well, I'll let you think about that and remind yourself, because the point here is that therefore we've identified a type of substituent that's going to push electron density towards something that would be an alkyl substituent, things like methyls. So once we understand this, we go back now to our discussion of dienes. We would therefore want to add potentially alkyl groups to the diene in order to make the dienes more reactive. So if I have the core diene like that, I could add a methyl group because the methyl group is pushing electron density there. And then, of course, if I can add one to have that beneficial effect, then, of course, it's probably even better if I can add two of them. And of course, that's not the only position where I can add them. I could add two alkyl groups like that. You see where they're going to be pushing electron density. Now, even better would be a situation like this, where I have in cyclic form, because in essence, you can think of this as an alkyl group pushing electron density that way and an alkyl group pushing electron density that way. And likewise, we could have the 6-carbon version of this, where you could, in theory, say, right, we have two alkyl groups that are pushing electron density in that direction. So alkyl groups are always very good at making these things very strong dienes. I could have, for example, this one, which is also fairly good one. Now you might say, but hold on, isn't oxygen more electronegative than carbon? And so rather than the inductive effect here would actually be to pull. But then keep in mind that the oxygen has lone pairs of electrons that it can push in that direction. And it's doing so towards the core diene part here. So therefore, that's going to be beneficial. So there you see examples of dienes that should be very reactive because they have groups on them that are pushing electron density and therefore making the diene more electron rich, which is what you want. What about dienophile? So we want the dienophiles to actually be electron poor. So we would want to attach things to them that would pull electron density. So if I have my basic dienophile here, for example, I could add a ketone. Why would that be something that would pull electron density? So the carbonyl bond is highly polar. The oxygen is far more electronegative than the carbon, so it pulls electron density towards itself. So the oxygen has a very strong partial negative charge, leaving the carbon of the carbonyl with a very strong partial positive charge. So the carbon then, because it's getting electron density pulled away from it by the oxygen, tries to compensate for this by in turn pulling electron density from this electron-rich site, and therefore it's going to make that more electron poor. So therefore, anything that has a carbonyl right there at that position is going to work. So for example, if I were to have an aldehyde there, that would work. If I were to attach an acid there, that would work. If I would attach an ester there, that would also make that electron poor, because each time what's happening is I'm pulling electron density away from the core dienophile part. I could, for example, attach a cyanide, and I'll draw it out this way to remind you that that has a partial negative and that has a partial positive. Now, just like in the case of the dienes, if one of these makes the dienophile electron poor, then clearly having two of them would be even better. So if I could, for example, have two carbonyls in the form of aldehydes like that, if I could have, for example, two nitriles like that, that would work. If I could have two esters, and I'll just draw the esters like that for short, then clearly that would also work. And just like in the case of the cyclic ones for dienes, similar situation would happen in the case of your dienophiles, because imagine if I could have something like this. Here's my dienophile, and I now have it in the form of a ring like that, and now have two carbonyls that are pulling. So delta plus here, both of them are actually pulling, and this is locked in the form of a ring, so that's actually very good. Quick thing, a dienophile doesn't have to be only a double bond. I could actually have a triple bond. So a very, very good and strong dienophile that's very frequently used in organic chemistry is this one. The only difference if I use a triple, have an alkyne instead of an alkene, would be the following. In the the Diels-Alder reaction that occurs here, if I have this, just use a regular diene, and it's now reacting with a triple. So I won't put any substituent, but we know the substituents would make it more strong. Just to show you the difference in what would happen here is, again, your diene will take a pair of electrons, push towards dienophile. 6 will take 2 pi electrons, move towards 1, and these are going to shift over. So what I'm going to end up getting here is going to be double bond here, but there will be a double bond there. So this will be 1, 2, 3, 4, 5, and 6. When I started off here with the dienophile having a double bond, you end up with a single bond in the product. And if I start with a triple bond, then I simply end up with a double bond, but that's a perfectly valid Diels-Alder reaction. So then here we see good examples of strong dienes and strong dienophiles. So hopefully this all makes sense. Now, another feature or requirement of your Diels-Alder reaction. So let's remind ourselves, put our basic Diels-Alder, which is this, reacting with that, electrons move over, and move over, and they do so when you warm this, and you end up getting your product here. Now, this arrangement of your diene is what you call an S-cis configuration, because I could also have this arrangement where the 1,3-butadiene is like that, and this is what you call the S-trans configuration. In the S-trans configuration, this one will not do, right? So this one doesn't undergo a Diels-Alder. So the question is why? Why would that not undergo a Diels-Alder? So the reason is actually very simple. So here's 1, here's 2, here's 3, and here's 4. So here is my dienophile, 5 and 6. So 1 can reach over and form a bond with 5. And here is the problem. 5 would have to form a bond with 4, and that distance is too far away for the overlap to actually be effective, and so it doesn't happen. That means then that my dienes have to be in an S-cis configuration for this to happen. But once we take that into account, there are certain considerations that we'll have to worry about. For example, if I were to have the dienophile here, and I were to put an alkyl group here, a methyl, and an alkyl group here, a methyl, we have a problem. The problem that we have is that I now have these two groups that are bumping into each other. And therefore, this is going to be unstable. And the reason, of course, is sterics. The sterics here is bad. We have the two methyl groups bumping into each other, trying to occupy the same volume of space. And so they're going to bump each other. So how does this molecule resolve that problem? Well, what this molecule is going to do is going to be that it's going to rotate. And we know that there's freedom of rotation about a carbon-to-carbon single bond. So you're simply going to get a rotation here. When you rotate, when you undergo that rotation, what's going to happen is, right, here's this one, and then this is going to rotate so that the double bond is now here. And if the double bond is now here, where does your methyl group actually end up? Your methyl group is going to end up here. But now you have relieved any sterics that you might have had between these two. So this one is going to be, so here, this is less stable when it's in the S-cis conformation, and this is more stable when it is in your S-trans. But in the S-trans, there is no Diels-Alder. This is the conformation required for a Diels-Alder. So you see, this wouldn't be a particularly good diene because of this fact that it actually prefers the more stable version of it is the S-trans. Now, it doesn't mean that this doesn't undergo the Diels-Alder totally, right? It just means that it doesn't really want to undergo the Diels-Alder, and what little Diels-Alder it undergoes, right, will be based on the small percentage that's in the S-cis. So you won't get very good yield. You have that problem, right? Now consider a situation like this one. If I have a methyl group here and the methyl group there, there is no steric problems at all. So this is in the S-cis, which is what you need for Diels-Alder, and this is actually stable. So therefore, this is fine. This will do it. No, you can actually end up with a situation that's even worse than the one that I used here to illustrate, because at least in the case of this one here, it will prefer to be in the more stable here, but a small fraction, a small percentage will be in the S-cis, and it can do a little bit of Diels-Alder. But consider a molecule such as this one. Now, the problem with this one is that if you really focus on the conjugated part, here, here, and here, you notice that this is in the S-trans configuration. What is the problem? There is no way this could actually do a rotation around that single bond. That will not happen because it's two rings that are fused. So this is actually locked in an S-trans configuration, and therefore it will never undergo any kind of Diels-Alder reaction. So those are considerations for when you are thinking of what are good dienes, what are good dienophiles. In the case of dienes, you also have to remember that the S-cis configuration is required, and if you have substituents, you might have a problem because of stability, depending on the orientation of those substituents. So that is something to keep in mind. All right, let us then examine some features of the Diels-Alder. let's look at the regiochemistry. All right. So this is what we mean by the regiochemistry. Suppose I have this diene, and I want to react this with this dienophile. So there are two ways in which this could actually happen. But in one of them, I will orient my dienophile like that. In the other case, I could orient my dienophile like that. What is the difference? The difference is the following. If I do the reaction here, this way, then my product is going to be this. So I'll go ahead and put numbers 1, 2, 3, 4, 5, 6, and that's strictly to keep track of them. So therefore, this is 1, 2, 3, 4, 5, and 6. So I know what's reacting with what. So 1 has the methyl group. Double bond is between 2 and 3. And 6 is the one that has the aldehyde. So I have that. Here, the reaction is going to be this way. So the product that I get, again, I will put numbers strictly to keep track of where things are. So you notice the 5s and the 6 don't correspond, but we're just keeping track. So this is 1, 2, 3, 4, 5, and 6. So you notice 1 has the methyl, and in this case, 5 is the one that has the aldehyde. So notice the difference. Your two substituents in the first case are 1, 2 relative to each other, but they are 1, 3 relative to each other. So you see the regiochemical outcome is different depending on how the dienophile orients itself. And the question you should ask is, well, does it make a difference? Wouldn't it work either way? And the answer is there is a preference. How do we know which of those will be preferred? So we do a quick analysis of the diene and the dienophile. Now remember, the diene one has to be electron rich, dienophile electron poor. So the diene is pushing electrons towards your dienophile. So what we would want to identify is which carbon in the diene is the one that's going to start the process. It should be the most electron-rich site, and which site, which carbon, if it's all carbons as in these examples, is it the one that's going to receive the 2 electrons from the most electron-rich site on the diene? It'll be the most electron-poor. So how do we determine that? Well, let's look at this particular diene that I have here. So if I have this methyl group is going to push electron density that way. That's going to start crowding electron density around the double bond. Remember, the double bond is already rich. So if I'm pushing electron density towards it, you're starting to get repulsion. That is solved, in essence, by these electrons moving over like that. And so as not to violate the octet here, these electrons here have to move over like that. So ultimately, where does the high concentration of electrons or electron density end up? And the answer is here. So therefore, this is your most electron-rich site on the diene. Now notice the difference. If I were actually having this one, in this case, when my alkyl group pushes electron density, then these electrons would move over on that carbon. Now, if you're asking, well, couldn't they move in that direction? The problem with that, think back to resonance, you would be breaking that bond. And if you break that bond, you've destroyed your diene, and therefore this isn't going to work. That is why the movement occurs the other way, which means that in this case, your most electron-rich site is going to be that carbon. Right? So you see how you can find that. Now, sometimes some people some sources. Some textbooks say just treat it as if it's a full-blown resonance situation, right? Meaning the following. If I think of, let's say, having more like a methoxy, in the case of the methoxy, the oxygen will push by resonance this way, which means those electrons move that way, which they move that way. So once again, just like this case, you see this carbon is your most electron-rich site. And then it might be easier to see the second case. If I have a methoxy here, and the oxygen moves electrons this way by resonance, remember in resonance, you cannot move sigma electrons, which is why you cannot break that bond. That is not allowed. So therefore, the only way you can accommodate that is by these pi electrons moving here. And that is going to be your most electron-rich site, which is what we're seeing here. So in other words, I'll erase everything here just to keep the one we're dealing with, right? So we've determined for the diene, in this specific case, what's the most electron-rich site. Then I look at my dienophile. If what I have is an aldehyde, partial minus, partial positive, as that carbon pulls this way, then the pull is going to go that way. Ultimately, this is the carbon that has nowhere to pull from. So this carbon is going to be the most, in this case, electron poor site. That's it. So then let's go back. I'll take off the highlight here so that highlight what I need to highlight. Okay, so this time, let's highlight what's the most electron-rich and electron-poor sites that we have. So this is the most electron-rich site. This is the most electron-poor site. This is the most electron-rich site. And that's the most electron-poor site. And you see how we can tell which one is going to be preferred. In this case, you notice that the most electron-rich site, which I've highlighted here, is starting the reaction and giving the electrons to the most electron-poor site, number 5. And the case on the right, however, the problem is the most electron-rich site, which is 4, is not the one that's reacting with the most electron-poor site. So therefore, this is not what's going to be preferred. This is how that one is going to occur. So on the other hand, notice if I had a different situation, what if I actually were starting with this? Well, we've already decided that this is the most electron poor rich site. So if I'm reacting with the same dienophile, I would want to set it up this way because this is the most electron poor site. Now the most electron rich reacts with the most electron poor, and the rest of the reaction continues. I always forget that, we're warming this to happen. So therefore, if we go 1, 2, 3, 4, 5, 6, simply for purposes of keeping tabs, then the regiochemistry is here 1, 2, 3, 4, 5, 6. The double bond is between 2 and 3. The methyl group here is on carbon number 2, and your aldehyde is on carbon number 5. So you're going to have this arrangement for this one. So that is what we mean by the regiochemistry. Now, final word here, obviously, if I were to have started with, let's say, a diene like that, then that diene is perfectly symmetrical. Does it make a difference if I were to say, I put it this way, versus if I were to say that I orient it this way? And the answer is no, because you have symmetry in your diene. Likewise, if I am reacting with a dienophile that is, let's say, like this, so I have, let's say, here and here, then again, you clearly see this is symmetrical. So it really makes no difference if I put it one way or the other, regardless of what your diene happens to be. So that is something to consider. Okay. Yeah. So then, what else do we consider when it comes to Diels-Alder? Well, let's consider stereochemistry. Let us go ahead. In fact, let me work a couple just so that you get the whole idea. So what if I am reacting? What if I'm reacting this and I'm reacting it with, let's say, there. Well, when this pushes, this is going to move that way. This moves that way. This would be the most electron-rich side. And when this pushes, you would also move this way. So that's clearly the most electron-rich. And when this pulls, this will be the most electron poor. So I've set it up exactly the way that it's supposed to be. So therefore, right, I'm going to get the reaction starting this way, that way, that way. When I do warming, again, keep tabs of your carbons when you're starting out so that you don't miss anything. So I get my 6-membered ring. So 1, 2, 3, 4, 5, and 6. 1 has a methyl group. Double bond is between 2 and 3. 3 has a methyl group, and 6 has your cyan. So that would be the product that you would end up getting there. If I start off with the same, let's say, just to give another quick example here, and let's say that I was starting off with this, which is itself symmetrical. So if that is symmetrical, right, there's no one way versus the other. So again, let's keep tabs. Let's say 1, 2, 3, 4, 5, and 6. So 4 reaches to 5, 6 to 1, and then the 5 electrons move over. So I form my 6-membered ring. 1, 2, 3, 4, 5, and 6. The double bond is between 2 and 3. 1 has an alkyl group, 3 has an alkyl group, and now there's a double bond between 5 and 6 here, and 5 and 6 each have an ester, so therefore my product, my Diels-Alder adduct would be this one. Okay, so a couple of quick examples just to make sure that we know how to write out the Diels-Alder. So we looked at regiochemistry. The next question is, what about stereochemistry? What considerations? So there are two things that we consider when it comes to stereochemistry. This reaction is what we call stereospecific. When we were doing reaction mechanisms, eliminations and substitution reactions, you will recall that, for example, when we looked at the E2 mechanism, we actually said that that's a stereospecific reaction because the antiperplanar requirement for the E2 meant that if I start with a given stereochemistry in my reactant, I'll get a specific type of alkene. I might get only the E or only the Z. So it's a similar situation here. So what we mean by that is the following. So we'll keep the diene simple so it doesn't cloud the issue here. Let's say that I was starting off with this diene of pile, dienopile. What you want to notice here is this is cis. You go back to the alkenes. So therefore, I can say, here's the reaction that's occurring. And therefore, what I'm going to end up getting is that at these two positions is where I have the aldehyde and nitron. So what's the relationship between those two? If I start off with a cis here, that relationship has to be maintained. So that means the aldehyde and the nitrile have to end up being cis here. So you'd get that. I could actually also show that and that. Now, in this case, what's the relationship between those two? Think back to your stereochemistry. If I put a pin through the one on the left and I flip it over like a pancake or a burger patty that way, do I get the same thing? That is what I want to figure out. Do I get the same thing? And what you will realize is you don't, right? So we get those. Now, if the reaction was here, but this time I have the trans dienophile. So notice this is trans. That relationship has to be maintained. So when the reaction occurs like this, I'll end up getting my product here, double bond, and this time the aldehyde and the nitrile are going to be trans to each other. So therefore, I'll show the outcome. So you notice if I begin with a cis dienophile, the relationship has to be maintained in the product. If I start with a trans, the relationship has to be maintained in the product. Now, notice that no textbook tells you, all right, well, what about the diene? Does that affect the stereochemistry? Because it can get more complicated, right? So, but I'll give you a quick little take-home message. If I start off with this, versus if I were to start off with those two alkyl groups where one is here and one is there. So we can say both of these are out. If we think of this as an inner cavity, then we say those two alkyl groups are out, but here one is out, one is in. So they're different. I'm showing one out, one in. What happens is that almost always, if both are out, these have to end up being cis in the final product, and these have to end up trans to each other. But now imagine if I'm looking at cis and trans for these, and cis and trans for the dienophile, then the question is, well, what's the relationship of these substituents relative to the substituents on the dienophile? In other words, what if this one reacted with the cis here versus if it reacted with the trans here? If we're now saying these here would have to end up being cis to each other, and these would have to end up being cis to each other, then the question is, well, what's the relationship between that and that and that and that? You see where it gets very complicated, which is why at this level we don't normally touch it. I think in the extra practice set that I normally give my classes, I do include one or two where you have to take that into account, and I'll show you the outcome. But we're the most, the thing that you have to be aware of is this one. What happens in the case of a dienophile, whether you begin with the cis or the trans. So that is the first thing that has to do with stereochemistry. The second thing, right, under stereochemistry is what we call the endo rule. Now, to begin the endo rule, to discuss it, I have to first remind you of bicyclic structures. So remember in Orgo 1, we looked at a structure like this, and we said that this structure is bicyclic. Or maybe one like this, we said bicyclic. So remember the structure here is these look like an inverted V. And so we can think then, if we have an inverted V, we can think of things that are going to be pointing towards the inner part, and we can think of things that are going to be pointing towards the outer part of that inverted V, right? And we call those orientations endo versus exo orientations. So for example, on this, anything substituent X that's pointing downwards like that, downwards like that, downwards like that, This would be the endo orientation. So here, this would be the endo orientation that you'd have at these positions. Then those things that are oriented this way, like that, like that, like that, this way, and that way, that is what we call the exo orientation. Now, when do you get bicyclic products? You only get bicyclic products when your starting diene is cyclic. Again, let me repeat that. You only get bicyclic products when your starting diene is cyclic. So notice in the examples that we've seen so far, and that's why I deliberately stayed from the cyclic dienes, that is not cyclic. So it's reacting with that. So here is your product that you're going to get. What you end up getting is not a bicyclic structure, it's just a cyclohexene, right? So that is not bicyclic. We don't have to worry about the endo rule here. When my starting diene, so let's say that I start off like that, and it's reacting with that. No, right? If I keep tabs, 1, 2, 3, 4, 5, 6, and 7. 4 will reach over to 6, 7 will reach over to 1, and then this is going to move over. So what I'm going to get here, and so I'll keep the perspective this way, which is why this isn't really a good way to do it, at least this perspective. What you end up having is the following: 1, 2, 3, 4, 5, double bond between 2 and 3. 1 is now attached to 7. 4 is now attached to 6. These are attached, and there is that. That is a bicyclic structure. Written that way, however, it's hard to see its bicyclic nature. So this is what you should really do if I want to show that reaction correctly. So I'll draw it again in flat form. This is reacting with that. So 1, 2, 3, 4, 5, 6, and 7. Now notice that number 5, right? This carbon really is not participating in the reaction, right? It ends up here. So to show a better perspective, really to be more accurate about this, it's better to redraw this. And the way to redraw it is to put the 5 out. So now there's 1, 2, 3, 4, and I've essentially removed 5 out of the way. And now it's actually, right, when we were looking at this perspective, remember, you might say, but hold on, wouldn't the problem here be that the distance for 7 to reach to 1 and 6 to reach to 4, they're too far apart, right? Which is the problem with an S-trans configuration. So if we redraw it this way, and I now put here, here's my 6, here's my 7, you see how much closer they are. 5 is really out of the way. So now when 4 reaches over and forms a bond with 6, 7 with 1, and the double bond changes position here, notice that you can readily see the bicyclic nature of this product. Here's 1, here's 2, here's 3, here's 4, here's 5, here is 6, and here is 7. The double bond is between 2 and 3, and 7 is the one that has the substituent. So let's go back to where I started up. What the heck is the endo rule? So the endo rule says, when my product is bicyclic, the preference is for substituents to be in an endo orientation. the preference is for substituents to be in an endo orientation. So let me show you what would be the endo and what would be the exo, just to remind you. So the endo would mean that my substituent is in that direction, because remember, the blue ones are the endo orientation. The exo orientation would mean that the aldehyde would be like that. So this is the endo-oriented constituent, and this is the exo. And the endo rule says when you get a bicyclic product, the preference is for substituents to end up in an endo orientation, endo orientation, right? And again, when do we have to worry about this? When my starting diene is cyclic, such as what we're seeing here. Notice again, to remind you, when my starting diene is not cyclic, such as here, there is no endo rule to worry about because the product is not a bicyclic product, right? So that is what we mean by the endo orientation. Now, I said the preference is, let's say that I was reacting this diene with this dienophile. So I'll redraw. Let me put numbers so we're keeping track of things. So you can tell 5 and 6 are not going to participate in this reaction, right? 7 and 8. So we can move them out. So the way I'm going to redraw this is this way, so that we clearly see 1, 2, 3, 4, 5, and 6. 5 and 6 are out of the way. And then I have 7 and 8. And notice that I have these cis. Notice that the dienophile is cis. So therefore, when 4 reaches over to 7, 8 reaches over to 1, and I move the position of the double bond here, this is what the product is going to look like, right? 1, 2, 3, 4, 5, 6 out of the way. And then, of course, we have 7 and 8. Double bond is between 2 and 3. Since my starting dienophile is cis, I have to maintain that, except in a bicyclic structure, it's not that they're going to be cis relative to each other. Maintaining the relationship means both of them will end up in the same orientation, either both endo or both exo. And what does the endo rule say is the preference? The endo rule says the preference is for them to be endo. So therefore, right, my two nitriles will end up in the endo orientation like that. That is what we mean. Now, suppose I was doing the same diene, here, but this time I am starting off with the trans dienophile. So you see here, they will not end up in the same orientation. So by necessity, one of these nitriles will end up in an exo orientation, because I have to I have to respect the initial trans, so they cannot end up oriented the same. So this time, in this case, notice when I get my final product here, one will be in an endo, but one will have to be in an exo. And that's just by necessity because we started off with the trans. So that's why I use the qualifying phrase, the preference is for these things to be endo. If there's only one of them, one substituent, such as we see in this case, then clearly that will prefer to end up in the endo, right? You will not want the exo. If I start off with the two substituents on the dienophile being cis, not a problem. They will both want to be endo. But if I start off trans, then one has to be endo and one has to be exo. So there's always that to consider. A couple more things, one more thing that I want to point out. So let's say that I had started off with the following. So let's say that's my diene, and this time, this is going to react with, let's say that. So 1, 2, 3, 4, I'll give 5 to the oxygen, 6 and 7. Redraw my starting diene here. 1, 2, 3, 4, and 5. Double bonds between 1 and 2, 3 and 4. That's now reacting with this, and I have this, so this would be 6 and this would be 7. So the reaction will be 4 to 6, 7 to 1, and the pi electrons move over. So what I'm going to get is a bicyclic product like that. But notice the following. I will have 2 double bonds, 1, 2, 3, 4. Oxygen is 5. This is 6, and this is 7. Now, where will your substituent end up? The thing to consider is what you already know about geometry based on hybridization. Carbon 6 and 7 in the product here and here are sp2 hybridized. If they're sp2 hybridized, they're planar. And remember, anything attached to sp2 hybridized carbons have to be on the same plane. So therefore, that cannot be at a right angle down, right, to be endo. It cannot be at an angle up to be exo. So you don't have endo or exo in a situation like this because the two carbons, 6 and 7, are planar. So if my molecule is like this, my 2 carbons, 6 and 7 are here, then anything attached to them have to be on the same plane. So we did try to show that something like this, that's neither exo, right? So this is neither endo nor exo, and that's because the carbon number 7 is sp2 hybridized, so it's really on the same plane, just going that way. It's not coming down endo, it's not going up exo, it's just going on the same plane. So that is something for you to know. Now, why is there a preference for substituents on the for the endo orientation? Let me try to draw it for you. First of all, let's remind ourselves, and we can do it just with this regular, right? This is the reaction that happens, and therefore I end up getting this product. So notice this bond is formed, that bond is formed. And of course, the double bond just changes position. Now, the important thing to notice is that these bonds that are formed here, they are single bonds. So therefore, they are sigma bonds. Same thing here. Now, see, this is where this flat perspective is a bit misleading the way we have it here, because it looks like I have a flat structure, and they're just doing overlap side to side. But side to side overlap would imply that I'm forming pi bonds. And yet what we're forming there are sigma bonds, and sigma bonds are formed by overlapping orbitals that are head to head, not side to side. That is important to actually take into account because it explains this. So we have here a 4-electron system, and we have a 2-electron system. You can see why we call this a 4+2 cycloaddition. So when it comes to my diene, 4 electrons, that means the 4 carbons are bringing their orbitals, 1 electron each, and they're going to try to overlap. 4 possible ways for this to happen, right, to lead to potentially bonding. So the best case scenario is this case where all of the waves have matching amplitudes and you overlap, and I get 1 orbital. Then I can get this situation where these two waves or these two carbons overlap and these two overlap, but there's a mismatch here. So there's a node. And remember, whenever you have nodes, that denotes instability. So that molecular orbital is less stable than the lower one. Then I can have this possibility where what happens is I have two nodes. And so the two nodes are going to be here and here to maintain symmetry, because we always like symmetry, which means this did not match this, but this one matched this, and that didn't match that. And then the worst case scenario that we can have is that none of the waves actually match in amplitude. So this one doesn't match this one, doesn't match that one, does not match that one. So therefore, you notice I now have not two, but I have three nodes. The more nodes I have, the more instability. So I'm getting less and less stable as I go up. And I have these and I have that. So I have one electron with each of these atomic orbitals. So that means when I fill orbitals here, molecular orbitals, 1, 2, 3, 4. So therefore, this represents the HOMO orbital. Now, if the diene is the one that starts off the reaction by pushing electrons in that direction, clearly it must push electrons from the HOMO orbital. That's the highest occupied molecular orbital. So those are the electrons that are the furthest away from the pulling influence of the nucleus. So they're the ones that will most readily be pushed towards your dienophile. Now my diene here, that's just two carbons that are coming to the game, right? Each one is bringing one electron. So when the waves for those two electrons try to combine, there are two possibilities. One is that you get matching, that is constructive interference. And so I'll have a molecular orbital here. And then I can get destructive interference when they don't match here and here. And then we see the node that we have here. And of course, we have molecular orbital. There are two electrons, so 1, 2. Now, the two electrons that the diene is pushing from its HOMO, right? Let's identify. This is therefore the highest occupied molecular orbital. This is the lowest unoccupied molecular orbital. So can the two electrons on the HOMO orbital from the diene be pushed to the HOMO orbital of the dienophile? No, because the HOMO orbital already has two electrons, and we learned a long time ago that the maximum number of electrons that can fit or exist in an orbital is 2. So therefore, the way this reaction happens is the two electrons from the HOMO orbital in the diene are going to be pushed or donated towards the LUMO orbital of the dienophile. Now, what I want you to actually see is that at the right here, let me just draw. So focus, what you want to do here is focus on the HOMO orbital and the LUMO orbital. Let me just point out that if we look at the two ending orbitals, the two ending parts of that molecular orbital, so this part and this part, you notice that one is shaded up and one is shaded down. When I look at the LUMO, same thing, one is shaded up and one is shading down. That is important. So the way the overlap actually occurs is more correctly shown like this. And again, you will have to bear with me as I try to. So right, so this will be the HOMO of my diene. And the HOMO of my diene, the one that's highlighted there, has shaded up, shaded up, shaded down, shaded down. My dienophile, therefore, cannot approach side to side. It actually approaches from below. Makes sense. So notice here in the LUMO, shaded up and shaded down. So therefore, I can show this one shaded up, and I can show this one that is shaded down. So what's happening here? Hopefully You can see this in the camera. Let me stop sharing. Maybe you will see it more. What I'm trying to emphasize here. So here, the dienophile, diene, and the dienophile are not approaching each other that way. Because if they approached each other that way, the orbitals would do side-to-side overlap. They have to be head-to-head. So what happens is the dienophile is here. Sorry, the diene is here. I'll put it this way. And the dienophile has to approach from below. By approaching from below, then the lobe here and the lobe here can do head-to-head. Otherwise, this way and they approach each other that way, it would be side-to-side overlap. So when they approach this way, you can see where the head-to-head overlap, and that's going to form a sigma bond. So going back to this, that's what I'm trying to show, but my drawing is really, really poor. So that's why I'm doing it this way. So when the diene approaches, it moves up, and as it approaches, you can see where these match and these match. But here is the thing, right? We have these orbitals in the back here and here. So my substituent can set itself up either of two ways, right? So in this case, the substituent we're talking about is so the reaction that's occurring, just to remind you, let's say, is actually this, and it's reacting with, and I'll put it down here. Let me just use this one, CN. It's probably easier for me to illustrate that. So there are two ways in which this can happen. The nitrile can set itself up this way. I have a carbon, and I have, try a different color, I might be able to show this more readily. And in fact, let me bring this a little bit closer so to give you a better perspective. So what's happening here is my dienophile is approaching this way, shaded up and shaded down. So as they come from this way, you can see head-to-head overlap, and it's matching. And my nitrile can set itself up this way. So carbon and nitrogen. Remember that those are triple bonds, so they have p orbitals. So therefore, I'll show it here for the carbon and the nitrogen. Let me try to draw this better. See, it's very hard. It's probably easier for me to just try to find a diagram to import, but I'll give it a shot here. So my nitrile, here's the carbon, and here's the nitrogen. No. And the nitrogen, let's say, is here. But these are sp hybridized, which means I can show an orbital up and down like that, up and down like that. And so you can get an interaction here and an interaction there. Now the alternative would be the following orientation. So I have my diene, just like that. Really bad at showing these things. So shaded up, shaded down. So now my dienophile can approach from below like that. So I can show shaded up and I can show shaded down, and you can see the head-to-head overlap. But the nitrile can set itself up this way. This way leads to the exo product. This way leads to the endo product. What you want to focus on is the two middle orbitals, this one and the diene. If my nitrile sets itself up that way, going underneath, then you notice that those orbitals on the carbon and the nitrogen of the nitrile here can interact. That interaction happens to be a stabilizing interaction. So therefore, this orientation is the one that is preferred, and that's the one that leads to the endo product. If my drawings are bad, you probably can look up a video. Okay, the Khan Academy, Leah Forsai, they have good videos which try to show a little simulation of this. You can see, but that's the reason why the endo rule actually holds. Quick thing here, and I'll be done. And that is, just as you can have a Diels-Alder, the opposite direction is actually quite easy to do. So when I go in this direction, right, I warm this up, I end up making my product, which is that. I can actually reverse this. So in that direction, so let me just maybe do it this way. In that direction, when you're warming, that's your Diels-Alder. So in the opposite direction, we have what we call the retro Diels-Alder. What would I do to the retro Diels-Alder? Because very often it's tempting to just say, well, if warming goes in one direction, cooling will go in the other direction. But not really. Let us look at, first of all, how does a retro Diels-Alder actually happen? So what happens is, and I'll put numbers here, 1, 2, 3, 4, 5, and 6. If I wanted to do a retro Diels-Alder, what I would do is reverse the steps. So notice that here is my step 1, 4 goes to 5, step 2, 6 goes to 1. The last step is the movement of the pi bond to change position of the double bond. So I'll start off with the last one, which is this, and I'll go in that direction, that direction, and that direction. And if I do that, I get that back, because notice that I will be breaking 1 to 6 and 4 to 5. I will be placing a double bond here, and that's what you see between 5 and 6. And I will be placing double bond here and here, which would be 1 and 2. So I get back those things. Another quick example. So let's say that I had the following Diels-Alder adduct. And let's say that I have that. What's the diene? What's the dienophile that actually gave rise to this? Well, start with this, and I'll show you that it doesn't make a difference if I do the movement up or down. So here, for example, I could move this way. These sigma electrons move that way. These sigma electrons move that way. So you notice, right, if you pay attention, I have broken that bond and I have broken that bond. So therefore, what this is going to do is, here, I now have a double bond here. Again, I will put numbers just to keep tabs. 1, 2, 3, 4, 5, and 6. So this is 1. There's now a double bond between 1 and 2. There's now a single bond between 2 and 3. There's now a double bond between 3 and 4. The bond between 4 and 5 is no longer there. 1 and 6 is no longer there. But I've now placed a double bond between 5 and 6. And 6 is the one that has the aldehyde substituent. So there's my diene, there is my dienophile. Let's say that my final product had actually been a bicyclic product like that. That's a Diels-Alder adduct. And let's say that I had right, these two being endo. Okay, so I'll start off with my double bond, move it back that way, which means I have to move these two here, and I have to move these there. So what I broke, notice, is that bond and that bond, right? So I want to put numbers to keep tabs. Let's say 1, 2, 3, 4, 5, 6, 7, and 8. So therefore, just keeping that, and I'll keep it the same orientation. So if I start with 2 to 1, there's no a double bond there. There's no a single bond between 2 and 3. There's no a double bond between 3 and 4. 4 is still attached to 5. 5 is still attached to 6, and 6 is still bonded to 1. There's no longer a 1 to 8 or a 4 to 7, but there's no a double bond between 7 and 8, and 8 has the aldehyde, 7 has the ester, and since they were both oriented the same way, both endo, I know that that had to have been a cis. So there be the diene and the dienophile that gave rise to that. Okay, so now we know how to actually, from a final Diels-Alder product, do a retro analysis, retro DA, and find what was the original diene and the original dienophile that gave rise to that. All right, knowing that, let us then look at this issue of, well, if we warm in order to go to do a Diels-Alder, are we just going to do the opposite and cool in order to get the retro Diels-Alder to go? Well, we can reason this out based on what we already learned in Orgo 1. So the thing to notice is the following. So let's analyze the Diels-Alder reaction. Then we look at the retro. So in the Diels-Alder reaction, notice that I am breaking two carbon-to-carbon pi bonds. Right? If you notice, I start off the reaction with 3 pi bonds, the ones that I've highlighted on the left. In the final product, I only have 1. So therefore, I actually broke 2 carbon-to-carbon pi bonds. Right? That's what I actually broke in the Diels-Alder. What did I actually form? I formed what? Well, I formed 2 new bonds. The 2 new bonds that I actually formed are my 2 sigma bonds that we get 1 to 6 and 4 to 5. So that means that I actually formed 2 carbon-to-carbon sigma bonds. Now, and by the way, when I say that I broke 2 carbon-to-carbon pi bonds, I don't mean that I broke the 2 bonds, right? If you look at the bond, let's say between 1 and 2, I had 2 bonds, and in the product, there's only 1 bond. So it's the second bond, the pi bond that I'm breaking. The sigma bond between 1 and 2, the sigma bond between 3 and 4, the sigma bond between 5 and 6, those are maintained. I'm just talking about the second bond, the pi bonds explicitly, specifically. So I broke 2 carbon-to-carbon pi bonds, the second bond, form 2 carbon-to-carbon sigma bonds. Which bonds are stronger, pi or sigma? Sigma, we already know that, right? When I break bonds, that's endothermic, I'm taking energy. When I form bonds, that is exothermic, I give up. So to break 2 pi bonds takes in less energy than the amount of energy that is given off when you form 2 carbon-to-carbon sigma bonds. I'll repeat that. Since sigma bonds are stronger, pi bonds are weaker, that means that the amount of energy it took to break the 2 carbon-to-carbon pi bonds is less than the amount of energy that is given off to form 2 carbon-to-carbon sigma bonds. So the net effect here is that for this, in the Diels-Alder, the delta H is going to be negative. The other thing to notice is that I'm going from 2 molecules on the left to 1 molecule on the right. So that means I'm going from more disorder to less disorder. Or in other words, I'm going from more disorder to more order. If that is the case, that means the change in enthalpy here is going to be negative. So that means if I'm looking at the retro-Diels-Alder, the exact opposite is happening. So in this case, to make a long story short, we can tell that the delta H is going to be positive. And since I'm going from 1 orderly molecule to 2 more disorderly molecules, that means I'm getting an increase in entropy, which of course is a positive value, right? So that's important. So then let's go back and do this very quick analysis that we did in Orgo 1. We know that the Gibbs free energy will be equal to the change in enthalpy plus minus temperature times the change in entropy. So then let's look at the Diels-Alder situation. In the Diels-Alder, will the delta G be positive or negative? So in the Diels-Alder, the delta H we determine is negative, plus the delta S is positive. If I have a positive delta S multiplied by a positive temperature, because that is in Kelvin scale, and I multiply by -1, then that means that will end up being positive. So that will be positive. In the retro Diels-Alder, what will the delta G be? So in the retro Diels-Alder, the delta H is positive, and if my delta S is positive, that means a positive delta S times a positive temperature times a -1, this will end up being negative. Now remember, high temperatures favor entropy, low to moderate temperatures favor enthalpy. So if I want my delta G to be negative, right? If I want my delta G to be negative, then in a Diels-Alder, I would want the enthalpy term to be bigger than the entropy because that's the one that is negative. And the enthalpy term is favored at low to moderate temperatures. So a Diels-Alder reaction is favored by low to moderate temperature. If I want in the retro Diels-Alder my delta G to be negative, then in that case, what I want is for my enthalpy term to be bigger than the, my entropy term, sorry, here, to be bigger than the enthalpy term. Entropy is favored by high temperatures. So to favor the retro Diels-Alder, I will prefer high temperature. So therefore, right, the Diels-Alder and retro Diels-Alder here are actually very easy to control, right? And we can tell that from our analysis. That means that the Diels-Alder, we really want to have low to moderate temperatures. So that's how we just warm, we get our product. If I were to overheat, then what would happen is the retro Diels-Alder would occur because this is favored at high temperature. So for Diels-Alder, we just warm, we don't heat at a high temperature, because yes, we might get the Diels-Alder, but at the high temperature, which favors the retro Diels-Alder, it'll just break apart and go back to the original starting diene and dienophyte. So that is always important to know what type of temperature favors which one. And that would be it. Working practice, working problems will help us to understand this some more. So that's it for Diels-Alder.